So I was asked to talk about usage models for GPU computing. And I thought what would be interesting to do is to divide this up into various sorts of sections. And think about, first of all, about how people are physically using and deploying GPUs, first of all. And we started with things like this. So this was an underground movement of university researchers who started taking their workstations and shoving GPUs into it. And you can see that there are cables hanging out to the side and extra fans bolted on to try and keep it all cool. And this was the way that some of the early people, and we're talking about maybe 4 or 5 years ago, the early way that people started using GPUs for scientific computing. Not very tidy, and so then we came along and thought, well, maybe it's a good idea if we try and make some sort of real decent products out of this. And the shock that was realized by people was, we're putting now gaming cards in the data center. I've been doing HPC for the best part of 20 years now, and I find myself working for a company that is now most famous for its gaming products. But nevertheless, there is a significant part of our business now in professional graphics and a growing business in professional applications of GPUs for scientific computing. But in the early days, we did hear this comment, people are putting gaming cards into the data center. And NVIDIA had, and still does, ship products like this, so racks, 1U rack mount systems, with, as you can see, 4 GPUs here, a lot of cooling along the front, and a big power supply to go with it. And the reason that we did this was because really to prove that there was a demand from the data center for GPUs for scientific computing. And in 2007, it was just NVIDIA shipping this sort of product with GPUs in a rack mount system. 2008, 2009, well, at least we persuaded one company that it was a good idea. And Supermicro is always very early, very quick off the mark with a new technology. They started producing these 1U servers containing both the GPUs and the CPUs in the single chassis. But by the time we get to 2010, we're now seeing that all of the major HPC vendors, and I hope that I haven't insulted anyone present in the room by missing off their logo, but I think the point is that all major HPC vendors are now shipping servers with GPUs integrated into them. So I can remember going to a supercomputing conference 3 or 4 years ago, and if you looked at the NVIDIA stand, there were people standing there saying, hey guys, we've got something interesting for you to look at. Whereas if you go to supercomputing in November of last year, you would have found that you could hardly get onto the NVIDIA stand for all of the activity that was going on there, for all of the interest that was shown, and for seeing GPUs all over the show floor at supercomputing. And so we've now moved from a strange and innovative idea of using GPUs in the data center to being now a mainstream technology. So mainstream, in fact, that the fastest machine in the world is now a machine with GPUs in it. More than 7,000 NVIDIA GPUs are installed in this machine in China. 3 out of the top 5 machines in the top 500 list now have thousands of GPUs installed in them. So that's a look at how you can actually deploy GPUs in a practical sense. What about the usage of them? How are they being used? Well, again, we've moved from the concept of a few esoteric university researchers porting their codes to the point where GPUs are now being used in a large scale by commercial companies. So looking at the top left of this drawing, what you'll see is an example from seismic data processing. The seismic data processing people were one of the earliest verticals to pick up GPUs as a practical way of processing their data. It so happened that the early GPUs we shipped didn't have all of the features that the scientific computing community would expect. So, for example, it only had single precision rather than 64-bit arithmetic. Nevertheless, given the quality of the data that comes out of seismic records, this 32-bit arithmetic was perfectly fine for their needs, and so they were very quick to pick up the technology of GPUs. But we see others here. So in the middle, we have here Procter & Gamble, molecular dynamics for designing, I think this was new soaps and new surfactants. Bloomberg, so they were monitoring data coming into their data centers, financial data coming into their data centers, and using that to process, make models of what's happening in the stock market. And a few others here. So this is a very interesting one. This is the pictures of the very first landing on the moon. And they record these images were recorded on tape. And one day an engineer had run out of backup tape, and so he picked up this tape, which he didn't think was very interesting, which had the original pictures of the moon landing on it, and he erased it and used it for backing up his data. And so we now had no copies of the original images of the first moon landing. So what happened was that this Lowry Digital company, they took the news coverage. So behind the newscaster's head, there were pictures being shown. These recordings of television broadcasts were still in existence. And so they took those images from captured off screen, processed the data, and in fact, they're rather an improved thing. So it doesn't look now rather better than it did when we saw it live in the 1970s, wasn't it? And then lots of other things, BAE Systems. This happens to be a project that I'm personally involved in. So because I work in Bristol, I live in Bristol, rather close to the British Aerospace Research Centre. So these are people using GPUs for doing CFD modelling. And so as you can see, there are plenty now of examples of real companies doing real work with GPUs. And when we get to organizations like ANSYS, I think we can now believe that the GPU has become mainstream. This is the major, one of the major CAE, computer-aided engineering pieces of software. 125,000 people using ANSYS, or 125,000 licenses. Many of those are probably site licenses, so many more users than that. But when we get to the point where organizations like ANSYS or Abacus or maybe Fluent in the near future, these major applications are using GPUs, I think we can then accept that GPUs have become a mainstream technology. Yet another example, MATLAB. MATLAB have now already announced that they have support for GPUs in their release from the end of last year. It was, I think, both MATLAB and NVIDIA will admit that this was just a show of intention. Nevertheless, what we have now is a commitment, there will be a commitment from MATLAB over future releases to include more and more GPU features within their products as time goes on. So MATLAB, a high productivity environment, not difficult to program, and giving access to people who are using these productivity languages, giving these people access to the power of graphics processors. What about using GPUs in complex systems? So a GPU, it started off really as something to go in your home PC. And sometimes we talk to people who are involved with writing, for example, the drivers here. And they say, oh, it only takes one click to install our driver. Well, that's fine if you've only got one machine to install it on, but if you want to install it on a 5,000 node cluster, you don't really want to have 5,000 clicks to go through to get the driver installed. And so NVIDIA has had over recent years to move from this concept of being a single device for a single PC to how can we work with the large clusters, how can we work effectively with large clusters and be something productive that can be used in the data center. And so many of the things that have been happening in the most recent release of CUDA have really been focused on efficiency, productivity, making things easier to use. Much of the base technology is now already in place, and now we want to make it effective and productive. And so we've got things, many new things in the most recent release to help with application porting, in particular how to use a single GPU in multiple threads and managing multiple GPUs from a single thread. Also faster and better multi-GPU programming, and I will talk about this in the coming slides. A technology called GPUDirect, we're now at version 2 of GPUDirect, which will help in moving data from one GPU to another within a node, and maybe in the future we'll get to the point of being able to move data directly from one GPU to another across a network. And also, of course, all the tools that people need. So it's not simply a case of handing a GPU to someone, a piece of hardware to someone and saying, here, get on with it. What you also need is all of the tools that go with that. So you need debuggers and profilers and libraries and all of the aids that the real programmer needs to deploy GPUs, to deploy his applications on GPUs. So first of all, let's think a little bit about GPUDirect. This is a technology with a roadmap. Version 1 was released already probably something like 6 months ago. And the purpose of GPUDirect version 1 was to improve the transfer of data between the GPU memory and an InfiniBand card. This really was the technological solution required here was to have the drivers of the NVIDIA card and the InfiniBand card cooperate with each other so as to remove some of the copies required in transferring data from GPU memory out to the InfiniBand network. And now we have this technology supported on both QLogic and Mellanox cards, Mellanox being the first to take up this technology. Version 2 now builds on that and works and extends it to look at the problem of how to move data from one GPU to another. And that will be illustrated in the next slide. So the initial way that we had to move data from GPU to GPU memory was via the host CPU. And so you would make, first of all, a copy from one GPU to the system memory of the CPU and then transfer it back into the memory of the second GPU. What we can do now with GPUDirect version 2 is make the simple single transfer directly from the memory of one GPU to another without passing through the intermediate stage of storing the data in the host system memory. One of the new technologies that's brought in that allows this is what we call unified virtual addressing. And so originally we had a separate address space for each of the GPUs and the host CPU system. What we have now is what's shown on the left-hand side, the right-hand side, in which we have set up within a node of the system a virtual single address space so that we have one unified address space across all devices resident within the node. And of course, this now simplifies the task of the programmer in many cases. Because if we have a pointer, we then know whether that pointer is in the CPU host memory, one GPU memory, or another GPU memory. And knowing where the pointer is, then libraries like MPI or other data passing libraries can examine the pointer and decide what is the right, can look at the source and destination pointers and do whatever is the right thing to get the data efficiently from GPU to one GPU to the other GPU or between the CPU and GPU. So this whole process now will simplify the programming task of the programmer as he tries to move data around the system. Really looking at improving programmer efficiency in as much as possible at this level in this release of CUDA. Thrust is another example of the sort of thing that we're doing to help productivity. So this is something that's rather similar to the STL library that's used in normal CPU programming. And so we can set up data structures for vectors on the host, vectors on the GPU, and set up algorithms to do manipulations of these sets of data. And then in a rather simple way, the programmer can write down what he wants to do and have that data transferred to the GPU, the algorithm executed, and the results returned back to him. So a way of improving the productivity of the programmer, again, using these templated libraries. Parallel Nsight. So what I'm finding now is that although the typical HPC community is much more focused on Linux than Windows, what I'm finding now is that many developers are starting to do their development in Microsoft Visual Studio and do the deployment in Linux. And the reason is that Visual Studio is a very effective and productive IDE for development of software. And so what we've done is we've complemented this by adding to Visual Studio Parallel Nsight. The Parallel Nsight integrates fully and seamlessly into Visual Studio, offering GPU debugging and profiling. And so yet another improvement to the programmer productivity. In fact, some people look at it and think, well, what have you done? It looks to me exactly like Visual Studio always does, except that now I can debug applications running on the GPU as well as the CPU. And that, in a sense, is a very good comment. If it's something that's very natural and something that's very familiar to the programmer, that's very, very, very good. Although, of course, it has taken us an enormous amount of effort to extract data from the GPU, to extract the state of the GPU, and present it within the Visual Studio IDE. And so, in summary, here we have a few of the things that we've added to CUDA in version 4 here. The whole goal of the evolution of CUDA is to push forward, add more and more things, making life easier and more productive for the programmer. What about the future? And this is the topic that was described in the program, and so I'll take a little more time to perhaps talk about it in more detail. So what we have here is a project that is being funded by the DARPA agency in the US called Echelon. NVIDIA is the lead of this project. But you'll see there are plenty of other big names in the field of high-performance computing. Cray in particular mentioned here, California University, Stanford University, and several important users. So Oak Ridge Labs, an important major user, of course, of HPC in the US. And the focus and the goal of this project is really to, not really to look at the exascale systems, but to look at what can we practically do in a single cabinet. So we're looking at putting a petascale system in a single cabinet and making that petascale system something practical that people can use in a very effective way. So this is a rough idea of what the concept might be. This is, of course, a research project. It's not intended to be any commitment to make any products. And I'm not going to be talking about my product roadmap here today. That would require NDAs from everyone. But this is a research project, and all of this material was, in fact, already spoken about by Bill Daly, our chief scientist, at the Supercomputing show last November. What you'll notice if we start on the inside here is on the processor chip itself, we have two sorts of processors. So we have, these that are labeled SM. SM stands for Streaming Multiprocessor, and this is the typical architecture that you will find within a graphics processor. It's an architecture that is intended to stream large quantities of data from the memory system through the GPU, doing processing in a data parallel fashion. And it's also an architecture that is very latency tolerant. It tolerates memory latency by being very multi-threaded. And so threads that are waiting for data can go to sleep and wait for data to turn up. Threads whose data has arrived in the processing core can wake up and start processing the data. So we have these highly parallel streaming multiprocessors. But of course, we know that not 100% of our applications are ever going to be massively parallel. There will always be some parts that have very modest parallelism or even are single-threaded. And so what we also need to do is to couple with these very highly threaded processors probably a small set of what we call latency processors. So processors that are optimized for low latency access. And this is rather like the typical CPU today. So the typical goal and concept of this traditional orthodox microprocessor is to process data with low latency from caches. And so we're always dealing with modest number of threads in modest-sized caches with low latency access to data that's in cache. And when we couple these two together, we're going to get the sort of architecture that will be appropriate for processing applications that will have large sections of massive parallelism and small sections probably of modest parallelism. And you might wonder what is the architecture that would be involved here. You may have heard recently that a large, significant court case was settled between NVIDIA and Intel. Nevertheless, that settlement didn't in any way allow us to make use of the x86 instruction set, and therefore we're looking for a rather different architecture here. And what I'm sure you will have heard is the announcement of Project Denver, which is a project intended to bring the ARM architecture into the field of high-performance computing. And so in the future, you could well be seeing products from NVIDIA coupling GPU-type architectures with ARM architectures for the more serial parts of the application. As you can see, we have a network on a chip here, and we have large caches. We have caches here, and eventually external RAM system, random access memory systems. And what we're aiming for here is to have within a single node something like 20 teraflops of performance in a single node containing a number of these chips, so maybe 8 or 16 of these chips or so, something like that, of that range. And then we put multiple nodes together to produce modules, and eventually assembling multiple of these modules into a cabinet. And the goal, if all things work out properly, is to have a petaflop or more within a single cabinet. The whole goal of this project is to look at how can we have a petaflop in a practical sense installed within a cabinet-sized rack unit. Something's happened here. Okay. Sorry?
Click on the screen.
Click on the screen? What's going to happen? Yes?
There you
go. Good question. I think that the majority of the flops are still going to be coming from the GPU-like units, but nevertheless, you do need, as you can see, we've got 128 of these streaming multiprocessors here compared with 8 of the other ones. So I suspect that still a large proportion will be simply from the GPU-like units. So whether we add another 10 or 20% from other stuff, it's not going to change the figures too much. Yes? Very good question, to which I don't know the answer because I've taken these slides from NVIDIA research, and there's still a few little comments scattered around the slides that I haven't quite got to the bottom of yet. One of the things that, if we think about some of the research projects that are going on in Europe right now, so one of the problems that we have with these very large exascale systems is going to be scheduling, so that the application needs to be a static scheduling is probably not going to be the best way to get full throughput of the system. We need to be able to react to what's happening at runtime and schedule appropriately. And I think this is the idea that they're talking about here, is that we need to be at runtime making decisions about what's happening on the system. Which is probably not a very good answer, because you have that question look still on your face, but it's probably the best I can do for the moment. So where were we? And then the idea is that once we have these cabinets with petascale or more systems of more performance in a single cabinet, then of course we can start to use these as building blocks for the very large exascale systems. Although the goal of this Echelon project is not really to put together a complete exascale system, but to work on what is the practicalities of a petascale system in a single cabinet. And as you can see, we're talking about now an exaflop, but also power. Power cannot be allowed to grow unboundedly in these very large systems. And one of the ways that we can, in some way, manage the power constraints that are available that are required to be able to reach the exaflop scale is to use GPUs and their very efficient mechanisms for generating flops in an efficient, power-efficient manner. And so I was expecting to speak for only 30 minutes rather than 45, but so I'm going to finish a little early. It gives plenty of time for discussion, should people want to have questions for me. NVIDIA, of course, has this conclusion. We see that GPU computing is already firmly on the map in high-performance computing. The number one of the top 500 list is a GPU accelerated system. 3 of the top 5 in the top 500 list are also using GPUs themselves. GPU computing does allow us to get to the exascale in a power-efficient fashion. GPUs do deliver flops in a very power-efficient way because of the concept of the design of the processors. The target and one of the key aims of Echelon and other developments within NVIDIA is to move away from the concept that the GPU is an accelerator that's plugged onto the side of the main processing unit. What you saw in the architecture of the Echelon system was that GPUs were firmly integrated into the center of the processor design, not something that was attached via an external peripheral bus. But as we know, I haven't talked about it today, but it's just another topic that I believe is going to be looked at within this Echelon research project, is how do we program these devices? At the moment, I don't think we've got anything real to say about that. NVIDIA does have plenty of ideas about how we're going to program these very large systems in the future. But really, this is one of the big challenges that the scientific computing community is going to have to face over the coming years, is how are we going to program these extremely large systems with probably hundreds of thousands, maybe even more threads executing on the system, very large numbers of processors and processing cores. So that concludes my presentation. If there are questions, I'd be happy to take them. Yes.
What would it take to utilize GPUDirect or simply linking with the right API libraries?
First of all, GPUDirect is 2.0 is already available in the GPU memcopy. So the GPU memcopy has a source and destination argument. And if the source and destination pointers are on different GPUs, then the data will be moved for you transparently. We are working with all of the major MPI implementations so that facility will be added into the MPI library so that, again, you don't have to worry about where the data is in your source and destination. Just provide 2 pointers and the appropriate thing will happen. If I remember correctly, I think we're working directly with the OpenMPI implementation. Maybe you can actually say more on this than I can, but I'm sure we're working with you as well on this project, and also the major commercial MPI implementations. I did bring this up with me and then forgot to show it. This is a very recent GPU board that is intended to go into some of these very new and dense server systems. So rather than having the orthodox PCI format, what we've done is reorganize the shape of it so it's a little bit more square. This makes it much easier for OEMs to include it inside their blade systems or in their dense 1U servers. And also, all of the connections, including the power, now just comes from the edge connector, so we don't need any external connectors. So this is a product that's, this is a board that's already shipping in T-Platform's servers, and will be seen in others coming soon in a server near you very soon. Yes.
What is the roadmap to integrate the GPU?
Well, I think you can see here that if you call that the CPU and this part the GPU, they are all together in a single network here.
Is that a virtual address space?
I think that we haven't yet decided fully exactly how it's going to be. I've seen all the variants on how you could do this proposed, and at some point we will reach a conclusion on the best way to do it. But it's not something that's fixed yet. We're far from shipping a product that will have this feature in it. And one of the things about NVIDIA compared with many companies is that we are quite agile. We can make changes in our architecture quite late in the process of the design process. And so even a few months before we start shipping things, we still have the ability to make changes. Probably not as significant as how we're going to connect a GPU and CPU together, but nevertheless we can make changes quite late in the process. Yes?
But so it sounds like the vision is you're going to run some general purpose? Or
well, we've recently Microsoft already announced at this Consumer Electronics Show, wasn't it? Microsoft already announced that they will be supporting Windows on ARM, and the requirements from the scientific community is going to be we have to support at least one of the standard distributions like Red Hat. Well, this is not particularly in NVIDIA technology, so the Dragonfly interconnect, the point is that if you have a very large system that's occupying, well, this room or maybe bigger, you've still got to be able to talk from the node that's in that corner to the node that's over in that corner. And the last thing you really want to do is to have a cable that's dragging all the way across the diagonal of the room. So the Dragonfly interconnect topology is a network topology that optimizes the maximum length of the cable you need to get the system fully connected.